Hello everybody and welcome to our 8th lesson in this course. What is dApp? dApp is a decentralized application consisting of such code that works in a decentralized blockchain network. Applications are usually divided into two main parts, back-end and front-end. According to this structure, the front-end is the external representation of the application, the interface and the client part of the application, while the backend is the internal implementation of the application, the hardware, software, and server part. Through tools and APIs, they interact with each other, and the front end uses the functions that the back end represents. The peculiarity of dApp is that the back end part is located on the decentralized network of the blockchain and is not located in any specific server. dApp features. The main process runs on the blockchain, has a published open source code that can work autonomously without control by any specific person or organization that would have privileged access. Often use their own tokens to interact with the application. dApp structure. Smart contract, blockchain intermediate layer, interacts with both the blockchain and other services. For example, a backend of a site or application. Backend provides functions for the front end of the application and also interacts with the blockchain through the layer. Front end. In other words, a decentralized application is an application whose main difference from others is the use of a smart contract in the blockchain as a backend. In order to integrate various components, decentralized applications often use message queues, subscription and sending systems, a cache, and various forms of databases. The design of a decentralized application can be of various types, but there are important conditions for ensuring the correct implementation. First, you need to consider how some decentralized applications will interact with others. This is required for dApps that are decentralized exchanges or name and application registries. Secondly, you need to consider how dApps work with their state modes. Sometimes it's necessary to provide a certain level of application modularity, for example, in cases where an extension of functionality is required or its improvement. This is necessary in order not to have to create a new version of the entire application for the sake of one change, because smart contracts in the blockchain cannot be changed, since the smart contract recorded in the blockchain is stored there forever. Types of dApps. Designing dApps can take several forms. There are, for example, important considerations in terms of how they interact with other dApps. For example, name app registries or decentralized exchanges, and how they work with their state over time. In some cases, some modularity might be desired in the event that functionality needs to be upgraded in the future without having to copy over state or re-register the dApp in registries and so forth. Some of these designs will be detailed here. Names and designs are a WIP. Edit where you want to. Closed system dApp. This is the most simple form, a dApp that is one contract and keeps all its state and function within it. Pros, simple to understand and design for. Cheapest, no requirement to talk to other contracts. Cons, immutable functionality. Once published, there is no way to change behavior. Closed system dApp with modularity on the edges. This is similar to the above. The app can function on its own but chooses to engage with other contracts. It's not required but adds additional functionality. A typical example is app name registries. Another example is a token that chooses to use a decentralized exchange like EtherX, where it's required to notify the DEX in the event that tokens have been deposited in its account. Same pros and cons as above, but usually these contracts are designed such that the owners can swap out or change various things in the contract it interacts with. For example, changing a name in the app registry or using a new decentralized exchange, the core contract stays immutable. Hooks. The dApps on the edges exists on their own. In some of these cases, hooks are required in your dApp to interact with them. The edge dApp is not responsible and doesn't want to be responsible to keep track of what happens in other dApps. If it was conferred new capability or tokens, it needs to be notified. EtherX is a good example of a hook. In a token dApp, the EtherX dApp can be given tokens and can then use them. But EtherX doesn't know about the token dApp. The important thing about hooks is that, again, it doesn't need to exist. Your dApp can function without it. Otherwise, it's just a normal transaction. Another token dApp hook could be it reporting information to a token registry. For example, if its nominal supply changes, it must notify the registry so that its information is correct. Multi-contract and multi-state. This is most likely what most complex dApps will look like. Concerns are separated in terms of functionality. Some parts are supposed to exist longer than others. They are dependent on each other for functionality. It's more an ecosystem with potentially different interfaces to it. An example is a prediction market that consists of multiple oracles that reveal information and contracts that sell and manage the shares of events. Another example is a game where the game world might consist of a tile per contract scheme and then confers rights to other contracts to change the tile according to some game rules. Modularity. For example, you don't have to build a future-proof token management system for selling shares in a prediction market, as it's expected to have a time limit. If new functionality is wanted, it can start with new bits. Cons, more expensive due to modularity. Hub and spoke. The hub and spoke pattern use modular, stateful spoke contracts for long-term storage and hub contract for access control to method interacting with spokes. The spoke contracts should contain only app storage and methods for accessing and mutating that storage. Private spoke modules should have a pointer to an owner or admin contract that points to a hub contract and stop execution when called from any other address. A hub contract contains pointers to these spoke contracts and may include some configurable properties that require some vote or permission or other logic to set. For upgradability, private spoke contracts may want to include a show method, callable only by the current hub, so the original hub contract can be swapped for a new contract. For a clean upgrade, the hub contract could include an upgrade method that, when passed the address of the new hub, will send that to the show method of all its spoke contracts, then auto-unregister itself from any registries. And finally, suicide itself or set a pointer to the new contract indicating its obsolescence. A potential use case for this pattern is to have contract factories spawn new hub and spoke contracts with some predictable makeup, only limited set of configurable elements, and optionally let the spawned contracts be added to a set of registries with data structures to efficiently support operations like search and or sorting. Therefore, these registries will contain only contracts with storage meeting some expected pattern. And by using an upgrade method that unregisters the hub contract from that set of registries, those registries can be guaranteed to list only valid contract addresses at any time. A hub and spokes pattern can also be supported by a core spoke contract with upgrade control over its own hub. For example, a token-based community has a core, its token balances. Apps are built on top of these for the token-based community. To interact with it, it goes through an administrator contract, the stateless functions contracts. In the future, it wants to upgrade its administrative functions and thus votes to swap out the current administrator functions for new one. Another example for this design is something like Republic of Doge, a DAO management system. It has a hub with pointers to spokes that can be various additional functionalities. However, it's not entirely similar since there the hub acts more as a name registry for interop between spokes which can be individually upgraded. Hub as a delegator only. In this design, the hub is only responsible for keeping track of permissions. Contracts are giving permission to manipulate state. Any other state besides mapping of permissions is kept in other contracts and are referable. So, In other words, you will have multiple state contracts and multiple function contracts. For example, function 1 could have permission to edit state of contract 1 and 3 and 5, while function 2 has permission to edit state of 1, 2, 4 and 7. Permissions can be revoked. This paradigm means that new functions can be built and old functions can be turned off. This also means any state required in the future can be tagged onto the delegator hub. A master function contract can optionally be added that determines how permissions are lent or revoked through owner or votes, for example. Hub and spoke pros and cons. Extreme modularity. The spoke contract should never have to change besides the pointer to its admin contract. The hub contract can unilaterally own the storage of its private spokes and can swap out all of its access control and functionality if desired. Although it won't work in all cases, hubs could support upgrading spoke contracts as well. If a hub wants to upgrade one of its spokes, it could upgrade itself to a new hub that includes logic for switching between spoke V1, spoke V2. It would likely need to support this logic in the UI as well. Cons. Upgrading hub contracts is do or die. If there is a bug, a bad address is passed, or it fails for any reason, spoke storage could get locked up forever. Both hub spoke upgrade patterns introduce an attack vector. If the upgrade access control is not sufficient, or if enough accounts controlling the hub decide to act badly, a subverted upgrade could lock up the app storage forever, sell it to a malevolent actor, steal ether from spoke contracts, etc. To prevent ether loss from spokes in such an attack, and thus eliminating much of the incentive for an attack, spokes containing ether or other tokens of value can use the origin or caller OP codes to define the account ID for withdraw or transfer methods. However, using origin does eliminate the possibility of contracts arbitrarily controlling their own balances. Potentially more expensive over time than copying state over. Possible incompatibility. Some dApps assume that both are in the same contract and thus could have potential issues in terms of who message sender is. For example, when interacting with external dApps. Now I would like to go on consider a complex dApp using the example of NeoSmart LOT, Internet of Things. This smart contract allows you to manage various devices. For example, kettles, refrigerators, light bulbs, sensors, video cameras. This system allows you to control devices from the blockchain. To manage such a device, the contract can be used as free, or it can take Neo or gas for a call. In order to use such a dApp, you need to embed in the blockchain a smart contract with a functional that processes incoming values and transfers them to LOT devices. By sending values to a smart contract through its functions, you can control the operations of the device. That is, a small amount of Neo or gas or other tokens can be sent to the contract in a transaction, after which that function on the device will be activated. You can also improve dApp which, to control the device instead of tokens, will use the parameters passed to it and then control will be free. Components. This dApp has 4 components: front end, smart contract, blockchain layer, and LOT device firmware code. The front end is developed on Node.js, which also uses the Chrome NeoLink extension to sign transactions. A blockchain monitor is used as an interlayer to track transactions and create an action queue. Smart contract, Ilcaro contract, contains information about the devices and costs that are necessary to use this contract. Elements. Let's look at the elements. In the web folder, we have front end written in JavaScript. Here we see the event subscriber neopubsub.py. This is a client written in Python and an MQTT server. It listens to events that come through runtime, notify and sends them to the MQTT chain to send them to LOT devices. Let's look at the structure of the client itself. The client contains a scNotify function which indicates the configuration with various parameters, a prefix function, and exit function. The def ecl handle publish function sends a message to the queue. Neo loop function save the blockchain to work with it. The def main function is used to run. Let's review the Ilcaro contract. At the very beginning of the contract, we see owner parameters, the ID asset to be used as a gas by the contract, in this case simply gas. The main def main method, we are already familiar with this from the previous lesson. It contains the modes in which the smart contract works. Verification checks who sent transactions. Application uses functions and parameters. Get value for transmission display. Put value for receiving and storing. Get press and put press necessary to indicate the price of the operation. LOT firmware. This firmware is written in C++ and it's designed for Node MCU devices. The code contains various connection parameters: MQTT server, connect, initial setting at startup, and loop mode that will switch when receiving transactions. In this lesson, we looked at the dApp architecture in the Neo blockchain. We checked the dApp types with different patterns for which applications can be written, and went through an example of one such application through which LOT devices can be controlled. That's all for today. Thank you for watching and see you in the next lesson.